Okay, hello, my name is Ben Kincade. I am a graduate student with Dr. Lubos Mitos's group in NC State University, where we develop correlation consistent effective core potentials. I've been doing this for a few years now. I was going to go ahead and just go over what we've done since the last QMCPACK workshop in 2021. There's actually been quite a few updates. So very briefly, I'm just going to talk about what effective core potentials are. Everybody in the room, I imagine, has some idea of what they are. The entire point of effective core potentials is to try and reduce the amount of electrons present in a calculation so that the cost of the calculation is reduced. So I have a list of a couple really common techniques for doing calculations, different methods that have different scalings with regard to the number of electrons present in the calculation. And these scalings get to be pretty large pretty quickly. They're like z to the 5.5 to the 6.5, z to the 6, z to the 7 with coupled cluster. And that gets to be intractable pretty quickly. So the entire goal of an ECP is to try and get that number z down to as low as we can get it. And the way that we can do this is we can replace many of the inner core electrons. Instead of fully simulating their presence in the core, we can replace them as a background and instead turn them into a potential. And I have a little schematic on the right side of the screen that kind of shows what this does. It removes some of the nodes and wiggles from the actual wave function so that it can more smoothly approach the, this is all within this R cutoff. So it only matches beyond R cutoff. It doesn't need to match inside that because all of the bonding properties happen at longer ranges. And the other thing that it does is it removes the Coulomb cusp present in the all electron potentials. I was just going to mention really quickly, normally you pick a core based on primary quantum number n. So for example, for the 3D transition metals, you are probably going to do a what we'd call a neon core, where n equals 2, that primary quantum number. You'd cut everything below that. So 2p6, 2s2, 1s would all be put into the core and effectively removed from the calculation. You would lose 10 electrons. So instead, for like manganese, you would only need 15. Okay. So Cody actually talked on some of this a little bit earlier, just before. I'll just briefly, I guess, talk about it as well. So a SOREP ECP, or a spin orbit relativistic effective potential, is going to do full spin orbit splitting. And how it does this is you have, or at least how we employ it, is with an AREP, or an average relativistic effective potential. And then we throw on spin orbit terms that we optimize separately. And then this is just the semi-local format for an ECP shown below, where you have a local potential. So this is the potential felt by the ith electron at location R. And it feels a local potential. All electrons feel the local potential in the same way. And then you have these non-local terms that only specific momenta feel. That's selected by L. All of our CCECPs are actually optimized against CCSDT, or coupled cluster singles, doubles, perturbative triples data, all electron data, in fact. And the spin orbit terms are actually calculated using COSI from Dirac with all electron again, and optimized against those. And we test them not only in the atomic spectrum, we try to create general effective potentials that can be used in a multitude of different applications. So we try and test them against the atoms with different gaps, and we also test against molecules for their general applicability. All right, and then of course we put them in quite a few different forms. So here's a very, very quick overview of what we've done in the last 2 years. Everything in red on the screen is what we have generated since the last workshop meeting. So we actually have a number of 3D elements. These were already present, but these are a new set of potentials that are, in fact, that are softened and adapted for solids and plane wave calculations. So these are meant to be more effective in those particular applications. I can talk a little bit more in depth about those shortly. And then we have fully generated from scratch spin orbit potentials for the 4D transition metals that are listed, as well as the 5D, bismuth, tellurium, I think iodine's off to the right. And then, in fact, we've branched out into some of the F elements following on Ghani's work, pioneering them with terbium. Okay. So I'm just gonna very quickly go over each one in turn. So here is the atomic spectrum performance for the 3D softened, the softened 3D transition metals. These are the mean absolute deviations. We're essentially finding the average error across the spectrum. And in green, I can't see underneath. In green is going to be our new softened CCECPs, and in blue we have our original traditional CCECPs. The main difference between these two is there is a slight accuracy discrepancy, but we think it's within acceptable means. The gray region on this graph shows you 1 kilocal per mole accuracy. So this is chemical accuracy. And so this discrepancy is barely noticeable, at least in this capacity. Where this discrepancy largely comes from is we weren't able to check as many states when we were optimizing. We couldn't ionize as deeply. Generally, when we're creating a new CCECP, we can ionize all the way down to the semi-core electrons and try and fit against every gap in between. With these, that becomes too difficult to do. So we had to eliminate a number of ionizations that we otherwise would have. For every single state shown, it was again done referencing coupled cluster all electron. Okay. Here are the parameters that we pulled out from the molecular binding curves. These are averaged across all of the transition metals that we actually devised these new softened CCECPs for. We have the bonding, or like the binding energy discrepancy. So all of these are mean absolute deviations, again, discrepancies. So the closer to zero, the better. So we have the binding energy, we have the bond length, and then we have vibrational frequency and the dissociation energy. And so we can see CCECPs are just a little bit closer to what you would expect, or they're at least a little bit closer to the all electron as opposed to CCECP soft, but it's very marginal. Almost all of them lay within the error bars of the other. I don't know if I mentioned this. These are all pulled from a Morse potential fit, and that is where we get these parameters and their discrepancies from. Okay, so here's the meat and potatoes of why we actually were trying to devise these new softened CCECPs. We were trying to confirm and create much softer variants of older CCECPs so that they worked better in plane wave applications. I'll show you on the next slide how bad that could be in some cases, but on this figure, this is essentially how we were calculating them. We would first do a reference energy, or we would take it to a really far cutoff. In this case, I think for this particular one, we were able to do 1,000 Rydberg, and it was pretty well converged at that point. And then we just essentially scanned through it every 10 Rydberg from like 300 to 500. And this gray region shows the region that we call converged. It is less than 1 millieV per valence electron within that band. And so for FeO in this case, it crossed that threshold at 430 Rydberg. Here's a full comparison of our softened CCECPs and their cutoffs in transition metal oxides compared with the old CCECPs. So our new CCECP softened versions are all sub 450. Rydberg in terms of their convergence in these solids calculations, whereas the old ones, some of them go up to 1500 Rydberg, which is just getting to be too expensive for any practical calculation that's running for a long time. So I'm now going to move on to the heavier elements on the list that we were talking about. Specifically, these would have been like some of the noble metals, gold, silver. All of them are listed at the bottom of the figure. So these are the atomic spectrum mean absolute deviations for those heavy elements. And we're actually comparing against quite a few things here. These are all the other like ECP tables that are currently widely used and easily available to check against. And in pretty much all cases, you can see our CCECP in green for each element is generally outperforming all of the other ones. It has a lower mean absolute deviation. And this gray line at the bottom, which is very thin at the moment, or at least on this slide, is the chemical accuracy region that we've seen on some of the previous ones. Overall, they show a pretty substantial improvement over previous ECPs that were available. So now this is another mean absolute deviation, but this is specifically just targeting in on a few very select important states. So these are the low-lying states. What we classified as the low-lying states are the electron affinity, the first ionization potential, and the second ionization potential. Those were the only ones included in this particular mean absolute deviation. And you can see again that in this case, our CCECP, all of them pretty much lie within chemical accuracy across the entire set that we tested. In red is the uncorrelated core, which is an all-electron method where you just don't fully correlate anything below what that would normally be put in the core of the ECP. And you can see that we're even outperforming that method, which you would expect to have a really pretty much as good a performance as you might hope. But in this case, our ECPs pretty much outperform them. Okay. This is a summarizing figure for that particular paper. We have in red the MADs for each core approximation. In blue, we have the weighted MADs, which is shown by this equation on the left. And then the LMAD, which is what I was showing on the previous slide. So the weighted MAD is a way of essentially determining the overall effects, or it's a way to gauge how well it performs on the low-lying states without disregarding the later ionizations as well. So it adds greater weight to the earlier low-lying states. So it kind of has this effect of smoothing out the MADs in general, is how it generally looks. And as you can see, in the case of all the ones tested for this particular paper, the CCECP pretty much outperforms all of them on all metrics, in some cases by a pretty substantial margin. I saw this figure earlier, and I think it was Paul's talk. This is the spin orbit. This is how spin orbit corrected the iodine dimer. So there's quite a few things going on in this figure, and I'll try and explain what they are. In anything shown in purple is the Stuttgart pseudopotential. Anything shown in green is our pseudopotential. Depending on if it's a circle or a square or an upside down triangle or a right side up triangle, it is going to be spin orbit or AREP. So the spin orbit calculation for the CCECP, the right side up triangle, you can see lies very close to this dashed red line that's horizontal across the screen. That is the binding energy experimentally determined. And then the vertical red line is going to be the bond length from experiment as well. And you can see that our vertical green dashed line is very, very close to like laying within the error bars of the experiment in this case. So we can see that spin orbit really corrects from our AREP case and moves us very close to the binding energy that we expect from experiment. So this is moving on to this is the same sort of figure I showed with the softened pseudopotentials, except this is now comparing all of the other tables. And as you can see at the very bottom, the CCCP performs as well or outperforms most of the other ones on this list. We can see that our discrepancy from the binding energy is around 20 millieV on average. Our bond length is within around 0.002 angstroms. And so we've really gotten very close to what we expect when we do all electron calculations. We're leaving very little on the table in terms of accuracy. So this is now moving on to our most recent work. These are yet new, different heavy elements. We added a couple more to the list, and these are a couple F elements. As you can see at the very end, we have gadolinium and terbium included in this set. So this is the same MADS format that we were seeing on a couple pages back. And you can see that our CCECP pretty much undercuts everything else and lays well below it, with a couple exceptions here and there. I will say that the F elements were incredibly difficult to develop, and in most cases took multiple months to actually try and do compared to some of the more conventional potentials that we have done. One thing of note is with these F elements, we were actually constructing them quite differently from how previous ones were done, where we would break them by primary quantum number n. Instead, we include the 4F into the valence, where normally we would try and put that in the core. Everything else in the n equals 4 shell was put into the core, except for just the 4F was moved to the valence. So here are the LMADs, the low-lying states for these, for all of the elements in this most recent paper. And you can see they lay well within chemical accuracy, with the exception being rhenium, but it seems that rhenium for most of the most ECPs move up quite a bit compared to some of the others. We're on par, at least, with the others on that regard. This is taking a more close look at the molecular binding curve discrepancies for gadolinium's molecules that we tested. So we tested gadolinium trihydride and gadolinium oxide using an uncontracted TZ basis set that was fully saturated. And in red, we have the uncorrelated core. We only had one group to compare against in this case with the same core as us, which was the SBKJC ECP. And you can see that in blue. And then our CC ECP is in green, as it's been on most previous slides. In both cases, we lay within chemical accuracy over most of the bond lengths tested. There was some weirdness with gadolinium as we got to really short bond lengths, especially in the hydride. It started to spontaneously jump to other bond states. There was some problems with trying to ensure that it always went to the same exact state between the all electron and then the effective core potential test case. So this is now just a summary figure of the molecular performance as we've seen for the other two sets. And we can see that we've got a relatively good performance when compared with the other ECPs tested against. However, this is going to be for the 4D metals. We could have generated this for gadolinium and terbium, but it would just be against ourselves, essentially. It would just be a list without much comparison, so we only did this one. So I'll just wrap up really quickly. In conclusion, we have created these new softened CCECPs for the 3D transition metals that are hopefully going to make it much easier to do plane wave calculations. They have way shorter cutoffs when compared with our traditional CCECPs. And then we have gone through and developed a number of heavy element ECPs that include spin orbit terms if you're interested in doing spin orbit calculations. And then we have now started to develop a couple F elements here and there as we've seen significant interest and have deemed them to be worth pursuing. All of these are either available currently or are going to be available very shortly on the pseudopotential library in a number of different formats, including UPF, MolPro, XML, whatever you can pretty much think of. For each element that is included within this set, there are going to be DZ and 5 zeta base up through 5 zeta base sets for each of them in those commonly used formats as well. Otherwise, I think that's pretty much what I have. So everything shown here is either currently published with JCP or is going to be, or has been accepted but hasn't been published yet. Okay. Thank you.
Thanks very much, Ben, for that comprehensive talk. Open for questions. I see Jaren's hand is up.
Hi, Ben. All your results look really great, and it's really exciting to see some of the heavier element potentials becoming available. One quick question I had, so out of that set you showed quite a few. Which of those kind of have the largest Z effective, and roughly how large is Z effective? That's maybe a very specific question, but even a rough order of magnitude would be good to know.
I want to say that the largest one that I can think of off the top of my head is going to be bismuth. And bismuth is, let's see, it's going to have a core of 60 and it's what, 83? So 23 electrons, I believe, in the valence. If those numbers are correct. 60 is definitely the core, though.
Hi, Ben. Really, really great work. So I don't know if you saw if it was on the slide, but did you benchmark those pseudopotentials with the ones against the ones that Jaren and Fernando developed a couple of years ago?
Okay, so that's for the transition metal oxide?
Like chromium, manganese, iron, like that first row up there.
So we actually ended up doing comparisons with those, but they look to be fairly different in terms of accuracy classes. We didn't end up including them in this one. They might be in the supplemental. If not, I have that data available. So
I guess another question I had too was, did you ever try benchmarking these potentials just at the DFT level against like what's out there right now, just in terms of like fast quantum espresso, like ultra soft pseudo potentials, that kind of stuff?
I don't think we've checked them that in depth against some of the other more common like DFT potentials. It could be done pretty easily though. They're in the formats ready to go. It would just be setting up a test set.
All right, thanks.
Mm-hmm.
All right, I see a question from Ye.
Oh, just following that, so about compared to DFT, I personally don't think it's really fair or necessary compared to other like ultrasoft, but there's one set, the SG15, that the norm conserving one specifically constructs for DFT. I'm wondering if our pseudo potential could be useful.
All right, my comment on this, I think there's a matter of philosophy here, and there's different approaches that one can take, right? Because Ben, correct me if I characterize this wrongly, right? This is an attempt to make the best pseudopotential reproducing the all-electron results, right? With the full many-body Hamiltonian done with the best solvers and so on. Whereas when you make a potential for DFT, you're trying to reproduce the properties of the atom for that particular functional that you're using. And that might be close, it might be different depending on the functional. And so you have to choose which path you want to take. So I think SG15 was done by fitting against lattice parameters of solids. That was the main thing, sort of novelty in that work, but it was still I want to say LDA and PBE at the time, right? So it's a different philosophy. I think the trick is just to say what you're doing and what your goals are in any work, so it's clear. Interesting question, though. Any more questions? Yes, there is.
Thank you for your presentation. Very nice. I have a question regard to the cutoff energy for the SOREP and AREP? Like, because you were showing large cutoffs, like what was it, 1300 for copper, or what is it for these new pseudo potentials?
So you're saying for the new ones that aren't shown on the list, not the softened ones? Okay, so the non-softened ones, like for these heavy potential or these heavy elements that we've done, they tend to be at or below 500. I know, for example, that gadolinium, I just did its cutoff like a week ago. It was 600, and that's on the high end. Pretty much everything should be at 500 below, probably closer to 400.
So this is more of an open, like, philosophical question, but often when we're collaborating with people who do DFT, they usually do all of their calculations and then say, okay, we're going to send you the structures, and these are the pseudopotentials that we used, which are usually not CCCPs. So in your opinion, what are some best practices to get data to align across QMC and DFT when we only have one type of pseudopotential?
That is a very good question, and I'm not sure if I know it well enough to commit to really comment too much. I've been very specialized with crafting these and like making sure that they align within all electron frameworks generally. I haven't had to do as much applied at the moment. So.
All right, I'll throw in 2 cents on this. I think this is actually a really good question. And there's different routes you can take. I would argue that each method should do the best it possibly can. And then the question is, do they agree not just with each other, but with reality, right? So if you're doing a DFT calculation, you probably want to use a PAW if you can, for example, right? That's going to be the most accurate, assuming you're going pseudopotential. You may even want to do all electron for some properties. And so we're not going to be able to make the same choices in QMC and of course other many-body calculations, but you want to use the best available route and choice of Hamiltonian in each. But maybe if you're doing a model calculation, you might want to take a different route so that the choices do align. All right, last call for questions. Perhaps someone online. Oh, there is a hand. Axa, please go ahead.
Yeah, I think this would be a silly question, but I just wanted to go ahead with this. For elements like alkaline elements, do you consider the core to be the element right before it? Like, for example, if you're looking at potassium, do you consider the core to be argon or neon? Because if we go to neon, it will give us more electrons available to ionize, right?
Yes. So generally for some of these, we actually do a couple different cores. That was especially true with some of the lighter elements. I think for even the aluminum series, this part of the main group, we actually have like a helium core as well as a neon core available. That can be very helpful in the case of like the alkaline. So for example, like sodium and so forth, that can be very useful to have a little bit more a few more valence electrons available. But we still produce them even with one electron in some cases.
Okay, that makes sense.